Introduction to HMAC. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are diving into one of the most fundamental and widely used tools in all of modern cryptography, HMAC, or hash-based message authentication code. You have likely heard of it in the context of APIs, JWTs, or secure protocols like TLS and IPsec. This presentation will be a comprehensive journey, starting from the basic need for message integrity and authenticity, exploring the cryptographic primitives that HMAC is built on, and finally, breaking down the HMAC construction step by step. By the end, you will understand not just how HMAC works, but why it was designed the way it was. The two core questions of secure communication. When two parties communicate over an untrusted network, like the internet, they need to answer two fundamental questions beyond just keeping the message secret. First, did the message I received get changed along the way? This is the problem of integrity. We need a way to detect if an attacker has tampered with the data in transit. Second, is this message really from the person I think it is from? This is the problem of authenticity. We need a way to verify the origin of the message and ensure it wasn't forged by an imposter. A Message Authentication Code, or MAC, is a cryptographic tool designed to answer both of these questions at the same time. What is a Message Authentication Code (MAC)? A MAC is a small piece of information, often called a tag or signature, that is generated from a message and a secret key. The sender calculates the MAC for their message using the shared secret key and attaches it to the message. When the receiver gets the message, they perform the exact same calculation on the received message using the same secret key. If the MAC they generate matches the MAC that came with the message, they can be confident about two things. First, the message has not been altered, ensuring its integrity, and second, it must have come from someone who possesses the secret key, confirming its authenticity. HMAC is a specific, standardized, and highly secure way to create such a MAC. The building block: cryptographic hash functions. To understand HMAC, we must first understand its core component, the cryptographic hash function. A hash function, like the famous SHA-256, is an algorithm that takes any input data, no matter how large or small, and produces a fixed-size string of bytes, known as the hash or digest. These functions have some critical mathematical properties. First, they are deterministic, meaning the same input always produces the same output. They are also one-way functions, which means it is practically impossible to reverse the process and find the input using only the output. Finally, a tiny change in the input results in a completely different output, a property called the avalanche effect. These properties make them ideal for building authentication codes. A naive and insecure attempt. So, why don't we just create a MAC by hashing the key and the message together? Our first straightforward attempt might be to simply concatenate the key and the message, and then hash the result. This would mean that MAC equals the hash of the key combined with the message. This seems plausible at first glance. An attacker without the key can't generate this hash, right? Unfortunately, this simple construction is dangerously flawed. Many common hash functions, due to their internal structure, are vulnerable to something called a length extension attack. An attacker who sees this MAC can, without knowing the key, sometimes calculate a valid MAC for a new message that consists of the original message plus some extra data they've appended. This completely breaks the integrity guarantee. What is a length extension attack? To understand a length extension attack, you need to know that many hash functions, like SHA-256, process data in blocks and maintain an internal state. The final hash is just the representation of that final internal state. An attacker who knows the hash of key message effectively knows the internal state of the hash function at that point. They can then use this state as a starting point to continue hashing new data they appended data. By doing so, they can calculate the hash of key pipe message pipe padding pipe appended data without ever knowing the original key. This is a catastrophic failure for HMAC algorithm, and it is the primary problem that HMAC was designed to solve. Another naive and insecure attempt. Okay, so what if we put the key at the end instead of the beginning? Let's try MAC equal hash open parenthesis message pipe key close parenthesis. This construction is not vulnerable to the length extension attack, which is an improvement. However, it has a different potential weakness. If the underlying hash function ever has a collision found, that is, two different inputs, M1 and M2, that produce the same hash, then this MAC scheme is broken. An attacker could replace message 1 with message 2 in transit, and since hash of message 1 concatenated with key would equal hash of message 2 concatenated with key, the MAC would still validate. While collisions are very hard to find in good hash functions, we want our MAC to be secure even if the hash function shows some minor weaknesses. The solution: HMAC. After seeing the failures of simpler approaches, we can appreciate the genius of the HMAC construction. HMAC solves these problems by using a nested, double hashing approach. It doesn't just hash the key and message once, it processes them through the hash function twice in a very specific way. The formula, at a high level, is HMAC equals H of key concatenated with H of key concatenated with message. By hashing the key with an inner hash, and then hashing that result again with the key, this method completely eliminates the possibility of length extension attacks. The internal state from the inner hash is masked by the outer hash, and an attacker cannot manipulate it. This nested structure has been mathematically proven to be a secure pseudorandom function, or PRF, which is the gold standard for HMAC algorithm. The full HMAC formula. Now, let's look at the full, formal definition of HMAC. It looks a bit intimidating, but we will break it down piece by piece. The formula is HMAC of K, M equal operator H of K XOR opad or H of K XOR IPAD or M. Here, H is our chosen hash function, like SHA-256. K is the secret key, and M is the message. K is the key after it has been pre-processed to be the exact block size of the hash function. The symbols opad, which stands for outer pad, and IPAD, which stands for inner pad, are special, fixed constant values. The XOR symbol represents a bitwise XOR operation, and the vertical bar symbol represents concatenation. In the next slides, we will walk through this formula one step at a time. Step 1. Key pre-processing K. The first step in an HMAC calculation is to prepare the key. HMAC requires the key to be exactly the same size as the block size of the underlying hash function. For SHA-256, the block size is 64 bytes. So, we have three cases for our input key K. If the key is longer than 64 bytes, we hash it first and then use the resulting 32-byte hash as our key. This is a crucial step for security. If the key is shorter than 64 bytes, we pad it with 0 bytes until it is exactly 64 bytes long. If the key is already exactly 64 bytes, we use it as is. The result of this process is our processed key, which the formula calls K. Why hash a long key? You might wonder why we hash the key if it is longer than the block size. Why not just use the first 64 bytes? This is a subtle, but important, security consideration. Some hash functions might have weaknesses if used with very long keys that share a common prefix. By hashing the long key first, we fold all the original key's entropy into a single, fixed-size, pseudorandom value. This ensures that the final key used in the HMAC calculation has no exploitable mathematical structure, regardless of what the original, long key looked like. It acts as a sanitization step, ensuring the key material fed into the core HMAC logic is of the highest possible quality. The inner and outer pads. Next, we need to define our two magic constants, IPAD and OPAD. These are not random. They are fixed values defined in the HMAC standard. IPAD, or inner pad, is the byte 0x36, repeated over and over to fill the block size, 64 bytes for SHA-256. OPAD, outer pad, is the byte 0x5c repeated to fill the block size. These values were chosen because they have a large Hamming distance from each other, meaning they differ in many bit positions. The purpose of these pads is to modify the processed key K in two different ways. One is for the inner hash, and one is for the outer hash. We will see this in the next step. Step 3. Creating the inner and outer keys. Now we use the pads to create two different keys from our single processed key K. The inner key is created by taking K and performing a bitwise XOR operation with the IPAD. The outer key is created by XORing K with the OPAD. The XOR operation flips the bits in K prime wherever the corresponding bit in the pad is A1. Because IPAD and OPAD are different, this process results in two derived keys that are related to K prime but are completely different from each other. This is crucial for the security of the nested hash construction. The inner hash. We are now ready for the first of our two hash calculations. We take the inner key we just created, K exclusive or IPAD, and concatenate it with the original message M. We then feed this entire string into our chosen hash function H. The result of this operation is an intermediate hash value. This hash value mixes the information from the key and the message together. However, as we saw with the naive H, K, M approach, this value alone is not secure. It is just a temporary result that we will use as the input for the final, outer hash. Step 5. The outer hash, final result. This is the final step. We take the outer key we created earlier, K exclusive OR OPAD, and concatenate it with the result of the inner hash from the previous step. We then feed this new, combined string into hash function H one more time. The output of this second hash calculation is our final HMAC tag. This outer hash serves to mask the output of the inner hash. It makes it impossible for an attacker to work backward from the final tag to figure out the intermediate hash value, which is what prevents the linked extension attack and other cryptographic breaks. The result is a secure message authentication code. Visualizing the entire flow. This diagram puts all 5 steps together into a single data flow. At the top, we start with our original key and message. The key is processed to become K, which is then XO-read with IPAD and OPAD to create the inner and outer keys. The inner key is combined with the message and hashed, producing the intermediate hash. This intermediate hash is then combined with the outer key and hashed a second time. The output of this final hash is the HMAC tag. This visual representation clearly shows the nested, two-pass structure that gives HMAC its strength. Technical example. Setup. Theory is great, but let's walk through a concrete, technical calculation from start to finish. For this example, we will use SHA-256 as our hash function. This means the hash output size is 32 bytes, and critically, the internal block size is 64 bytes. We will use a very simple secret key, the 4-byte string key. We will also use a simple message, the 11-byte string, hello world. Our goal is to follow the HMAC steps precisely to calculate the final authentication tag for this key and message. Example step. Key processing. Our first step is to process the key to make it exactly 1 block size long. The SHA-256 block size is 64 bytes. Our key is key, which is only 4 bytes long. According to the HMAC rules, since the key is shorter than the block size, we must pad it with 0 bytes until it reaches 64 bytes. So, our processed key, k, becomes the 4 bytes of our key followed by 60 null bytes. This 64-byte value is what we will use for the rest of the calculation. This step ensures that no matter what size the original key was, we are now working with a key of a consistent, known length. Derived keys. Now we create our inner and outer keys. We take our 64-byte processed key k and XOR it with the IPAD and OPAD constants. The IPAD is the byte 0x36 repeated 64 times. When we XOR k with IPAD, the first 4 bytes change, and the remaining 60 bytes are all 0x36. This gives us our inner key. The OPAD is the byte 0x5c repeated 64 times. When we XOR k with OPAD, the first 4 bytes change differently, and the remaining 60 bytes are all 0x5c. This gives us our outer key. We now have 2 distinct 64-byte keys derived from our original secret. Example step. The inner hash. This is the first hashing pass. We take the 64-byte inner key we just calculated and concatenate our 11-byte message, "Hello World," to the end of it. This creates a 75-byte string that will be the input to the SHA-256 function. We feed this 75-byte block of data into SHA-256. The output is a 32-byte digest, which is our intermediate hash result. This result is shown on the slide in hexadecimal. This value has successfully mixed our key and message, but it is not yet secure enough to be our final tag. The outer hash. This is the final step of the calculation. We take the 64-byte outer key that we calculated earlier and concatenate the 32-byte intermediate hash result to the end of it. This creates a 96-byte string. We feed this final 96-byte block of data into the SHA-256 function for the second and last time. The output of this hash is our final, 32-byte HMAC tag. The hexadecimal value shown on the slide is the correct HMAC SHA-256 tag for the key and the message "Hello World." Example summary. Let's quickly recap the entire calculation flow we just performed. We started with a short key and padded it to the 64-byte block size. We then used IPAD and OPAD to create 2 distinct keys. The first key was hashed with the message to create an intermediate result. The second key was then hashed with that intermediate result to produce the final, secure tag. This step-by-step process, while complex, is what every standard HMAC library does under the hood. It is this precise, multi-stage operation that provides the strong security guarantees that make HMAC so trusted. Security properties of HMAC. So what does this complex construction actually achieve? The primary security goal is that HMAC should be a pseudorandom function, PRF, as we have discussed. This means that to an attacker who does not know the key, the output of HMAC key message is computationally indistinguishable from a truly random string of the same length. This is a very strong guarantee. It implies that an attacker cannot forge a valid MAC for a new message, nor can they learn anything about the secret key from observing any number of message MAC pairs. The security of HMAC has been extensively studied and is proven to be secure as long as the underlying hash function is secure. Security against forgery. Let's be more specific about what secure against forgery means. A MAC algorithm is secure if an attacker, even after observing a large number of messages and their corresponding valid MAC tags, cannot produce a new, valid, message MAC pair for a message they have not seen before. Because HMAC is a PRF, its output looks random. The attacker has no better strategy to create a valid tag for a new message than to simply guess a random value. If the tag is 256 bits, from SHA-256, the probability of guessing correctly is 1 in 2 to the power of 256, which is astronomically small. For all practical purposes, it is impossible. Security even with hash function weaknesses. One of the most powerful features of the HMAC construction is its resilience. The security of HMAC does not require the underlying hash function to be perfect. For example, even if the hash function is vulnerable to collision attacks, where an attacker can find two messages M1 and M2 that hash to the same value, the HMAC construction is often still secure. This is because finding a collision in the hash function does not necessarily help an attacker break the PRF property of the HMAC wrapper. This resilience is extremely valuable, as it means HMAC can remain secure even if new, minor weaknesses are discovered in hash functions like SHA-256 in the future. Practical example: JWT signature. Let's look at a very common real-world application: JSON Web Tokens, or JWTs. A JWT consists of a header, a payload, and a signature. To ensure the token hasn't been tampered with, the signature is often an HMAC. The server takes the base 64 encoded header and payload, joins them with a period, and uses this string as the message for the HMAC function. It uses a secret key that is known only to the server. The resulting HMAC tag is then attached as the signature part of the token. When the server receives a JWT from a client, it recalculates the HMAC and verifies that it matches the signature. If it does, the server knows the token is authentic and its contents can be trusted. Choosing a hash function. The H in HMAC stands for hash, and you must choose which hash function to use. The security of your HMAC tag is directly tied to the security of the hash function you select. In modern applications, you should almost always choose a member of the SHA-2 family. HMAC SHA-256 is the most common and widely supported choice. It provides a 256-bit security level, which is more than enough for the vast majority of applications and is expected to be secure for many decades. For extremely high security or long-term archival purposes, HMAC SHA-384 or HMAC SHA-512 can also be used. You must never use older, broken hash functions like MD5 or SHA-1. Truncating HMAC output. An HMAC SHA-256 tag is 32 bytes, 256 bits long. In some applications, particularly where bandwidth or storage is very constrained, it might be desirable to use a shorter tag. Is it safe to truncate the output? The answer is yes, with a very important caveat. Truncating the tag reduces the security level against a brute force guessing attack. If you truncate the output to the first 16 bytes, or 128 bits, an attacker's chance of guessing a valid tag goes from 1 in 2 to the 256th power to 1 in 2 to the 128th power. While still astronomically small, it is a reduction in security. The standard recommendation from NIST is that the output should never be truncated to less than half the length of the hash output. And for most cases, it should not be shorter than 128 bits. HMAC versus digital signatures. It's important not to confuse HMAC with digital signatures, which use public key cryptography, like RSA or ECDSA. Both provide integrity and authenticity, but they have a key difference: non-repudiation. HMAC uses a symmetric, shared secret key. Both the sender and receiver have the same key. This means either party could have created the MAC tag. You cannot prove that the sender, and only the sender, created it. Digital signatures use a private/public key pair. Only the holder of the private key can create the signature, but anyone with the public key can verify it. This means the sender cannot later deny having signed the message, a property called non-repudiation. HMAC does not provide this. HMAC in TLS. HMAC is a critical component of the Transport Layer Security (TLS) protocol, which secures most of the Internet's traffic. In older versions, for example, TLS 1.2, an HMAC function, like HMAC SHA-256, was used in a construction called encrypt then MAC. After the data was encrypted, An HMAC tag was calculated over the encrypted data and attached. This provided a very strong guarantee of integrity for the encrypted records. In modern TLS 1.3, dedicated authenticated encryption with associated data, AEAD, ciphers like AES-GCM are used instead. However, the HMAC function is still used pervasively inside the TLS 1.3 key schedule. The entire process of deriving session keys uses HKDF, which, as we know, is built entirely on HMAC. HMAC in IPsec. Another major use case for HMAC is in the IPsec protocol suite, which is used to create secure virtual private networks, VPNs. IPsec can operate in two modes, and HMAC is used in both to provide integrity and authenticity for IP packets. In the authentication header, AH protocol, an HMAC tag is calculated over the entire IP packet, including most of the IP header. In the encapsulating security payload, ESP protocol, the payload of the IP packet is first encrypted, and then an HMAC tag is calculated over the encrypted payload. In both cases, HMAC SHA-256 is a common choice, ensuring that VPN traffic cannot be tampered with by an attacker on the network. The importance of the key. The security of HMAC rests entirely on the secrecy and quality of the key K. If an attacker can guess, steal, or otherwise learn the secret key, the entire system is broken. They can now generate valid MAC tags for any malicious message they want, completely defeating the purpose of the algorithm. Therefore, key management is paramount. Keys must be generated using a cryptographically secure random number generator. They must be long enough to be unguessable. 128 bits is a minimum, and 256 bits is standard. And most importantly, they must be stored and transmitted securely, never exposed to unauthorized parties. Constant time comparison. A subtle but critical detail when implementing HMAC verification is how you compare the MAC you calculated with the MAC you received. A naive byte-by-byte comparison, like using the equal operator in many languages, can be vulnerable to a timing attack. Such a comparison often returns false as soon as it finds the first differing byte. An attacker could send millions of invalid MACs and measure the response time. A slightly longer response time might indicate that they guessed the first byte correctly. By repeating this process, they could potentially recover the entire MAC byte by byte. To prevent this, cryptographic libraries provide a special constant time comparison function that always takes the same amount of time to execute, regardless of how many bytes are correct. Other types of MACs. CMAC. While HMAC is the most common hash-based MAC, it is not the only type. Another important standard is CMAC, or cipher-based MAC, which is built from a block cipher like AES instead of a hash function. CMAC works by encrypting the message in blocks, using CBC mode, and using a part of the final encrypted block as the tag. It is provably secure and can be very efficient on hardware that has AES acceleration. HMAC and CMAC are both considered highly secure, and the choice between them often depends on the primitives available and performance characteristics of the target platform. The PRF property in detail. Let's go one level deeper on the PRF property. The security of HMAC as a pseudorandom function is what allows it to be used for more than just authentication. It allows it to be used as a building block for other cryptographic systems, most notably key derivation functions. Because the output HMAC-KM appears random, we can use it as a source of pseudo-randomness. By feeding it a secret key K and a changing input M, like a counter, we can generate a stream of unpredictable bytes. This is exactly what the HKDF expand function does, using HMAC as its engine to generate new keys. HMAC and HKDF. As we saw in a previous presentation, HMAC is the mathematical heart of HKDF. The HKDF standard is essentially a specification for how to use HMAC in two specific ways to achieve key derivation. The HKDF extract step, where PRK equals HMAC of salt and IKM, uses HMAC to concentrate the entropy of an initial secret. The HKDF expand step, where Tn equals HMAC of PRK and Tn-1, uses HMAC iteratively as a PRF to generate a keystream. Without the proven security and PRF properties of HMAC, the entire HKDF construction would not be secure. The inner hash. Let's review the purpose of the inner hash one more time, as it's the first critical step. The calculation is H open parenthesis K prime XOR IPAD pipe M close parenthesis. Its job is to create a digest that combines the secret key with the message. By XORing the key with the inner pad, we create a derived key that is used for this initial pass. This step is what primarily provides the integrity protection. Any change to the message M will cause this intermediate hash to change completely. However, this result is never exposed directly. Review the outer hash. The purpose of the outer hash, H of K XOR opad concatenated with the result of inner hash, is to provide the security guarantee that makes HMAC a true PRF. It effectively acts as a protective shell around the inner hash. An attacker cannot reverse this outer hash to learn about the intermediate result. This is what prevents linked extension and other attacks where an attacker tries to manipulate the internal state of the hash function. The outer hash finalizes the process and produces the secure tag that can be publicly shared. Key length versus security level. The security level of HMAC is determined by two factors: the size of the hash output and the length of the secret key. The security against a brute force attack on the key depends on the key's length and entropy. The security against guessing the tag depends on the tag's length, which can be truncated. The overall security is generally considered to be the minimum of these values. For HMAC SHA 256, the hash output is 256 bits. If you use a 256-bit key with high entropy, you achieve a 256-bit security level, which is exceptionally strong. Using a key shorter than 128 bits is not recommended. HMAC in API authentication. Many web APIs, especially those used for server-to-server communication like AWS APIs, use HMAC for request signing. The process is typically more complex than a simple JWT. The client will create a canonical representation of their request, including the HTTP verb, path, query parameters, headers, and the request body hash. This entire string becomes the message for the HMAC calculation. The client signs this canonical request with their secret API key. The server on the other end reconstructs the exact same canonical request string from what it received and computes its own HMAC. If the tags match, the server knows the request is authentic and has not been tampered with. The letter H in HMAC, a generic construction. It is important to remember that HMAC is a generic construction. It is a recipe that tells you how to build a MAC using any cryptographic hash function. While we have been using SHA 256 as our main example, you could theoretically create HMAC SHA 3256 or HMAC Blake 2B. The security proof for HMAC holds as long as the chosen hash function meets some basic cryptographic requirements. This makes the HMAC construction very future-proof. If a new, better hash function is invented tomorrow, we can immediately start using it within the existing, proven HMAC framework to create a new, even stronger MAC algorithm. Why not HK or MRK? One other seemingly plausible construction involves sandwiching the message between the key, hash of key, message, and key. This is known as the envelope method. While it's much better than the simple prefix or suffix methods, it has still been shown to be less robust than HMAC. Under certain theoretical conditions, if the underlying hash function's collision resistance is broken, this construction can become vulnerable in ways that HMAC is not. The specific use of the inner and outer pads, IPAD and OPAD, in the HMAC standard was chosen because it provides the strongest possible security guarantees based on the weakest possible assumptions about the hash function. HMAC and random number generation. The PRF property of HMAC makes it a suitable component for constructing a deterministic random bit generator, or DRBG. A DRBG is an algorithm that can produce a stream of cryptographically secure random-looking numbers starting from a secret seed. The NIST SP 800-90 standard specifies an HMAC DRBG. It works by maintaining an internal state, and when new random bytes are requested, it calculates HMAC key state to produce the output. It then updates its internal state by feeding the output back into another HMAC calculation. This is a robust way to generate random numbers for cryptographic applications. HMAC. Standardized and trusted. HMAC is not some obscure or experimental algorithm. It is a mature, widely vetted international standard. It was invented in 1996 and is specified in multiple standards, including RFC 2104 and FIPS-PUB 198-1. It has been subjected to decades of intense cryptographic analysis by academics, governments, and industry experts around the world and has stood the test of time. When you need a message authentication code, HMAC is almost always the correct, safe, and standard choice. Its robust design and long history of security make it one of the most trusted primitives in applied cryptography. A note on implementation. One of the most important rules in cryptography is don't roll your own crypto. This applies strongly to HMAC while the algorithm is public. Implementing it correctly and securely is full of subtle pitfalls, like the need for constant time comparison. You should always use a standard, well-vetted cryptographic library provided by your programming language or platform. These libraries have been written by experts and subjected to extensive testing and review, ensuring that you get the full security benefits of the HMAC construction without introducing dangerous bugs. The big picture: integrity and authenticity. Let's return to our two original questions. By producing a tag from a message and a secret key, HMAC provides definitive answers. If the tag is valid, we know the message has not been changed, giving us integrity. And because generating a valid tag requires knowledge of the secret key, we know the message must have originated from another party who also holds that key. This provides us with authenticity. HMAC is a complete and robust solution for message authentication. Performance considerations. From a performance perspective, HMAC is extremely efficient. Its total computation time is dominated by the two hash function calls it performs. Hash functions like SHA-256 are highly optimized and are often accelerated in hardware on modern CPUs. As a result, calculating an HMAC is a very fast operation, typically taking only a few microseconds for reasonably sized messages. In almost all real-world applications, from web servers to embedded devices, the cost of HMAC is negligible and is never a performance bottleneck. Future of MACs. The future for HMAC is very secure. Because it's a generic construction, it can easily adopt new and improved hash functions as they are developed. We can already create HMAC SHA-3, for instance. At the same time, other types of MACs are becoming more common, particularly those that are integrated into authenticated encryption, AEAD, ciphers. For example, the ChaCha20 Poly 1305 cipher uses a special polynomial-based MAC called Poly 1305. However, when a standalone, general-purpose MAC is needed, HMAC remains the undisputed gold standard. Final summary. In this presentation, we have seen that HMAC is the definitive solution to the message authentication problem. It was designed specifically to overcome the security flaws in simpler hash-based constructions. It achieves its security through a proven, nested double hash design that has been shown to be a secure pseudorandom function. This makes it robust, versatile, and the ideal foundation for other cryptographic primitives like HKDF. It is, without a doubt, a fundamental building block of modern digital security. Conclusion. In the world of cryptography, simplicity is often a virtue. HMAC is a testament to this principle. By combining a standard cryptographic hash function with a simple, clever, and mathematically sound nested construction, it provides a powerful and versatile tool for ensuring data integrity and authenticity. From securing your web browsing with TLS, to authenticating API's requests, to forming the foundation of modern key derivation with HKDF, HMAC is a quiet workhorse that plays a critical role in securing our digital lives. Understanding its design is a key step in understanding modern applied cryptography. Thank you for your attendance. Please consider subscribing to the channel.